number 21. QNH is given to you. What is the pressure altitude at an elevation of 25,000 feet? Okay, so let's draw the diagram. So here is your airport. Let's say this is your airport surface. Okay, mean sea level QNH. Now elevation of this QNH is 999. We have to find out pressure altitude. Now pressure altitude is always measured from a standard pressure setting datum 1013. Now 1013 pressure is more than 999. So that pressure datum or that pressure value will be found below this mean sea level pressure. So I am drawing the standard pressure setting datum here. One zero one three. Okay, standard pressure setting 1013. Next, elevation is 25,000 feet. Elevation is 25,000 feet. Elevation is always measured from mean sea level. So that is 25,000. The pressure altitude is always measured from 1013 pressure datum. So that is this one. Okay. So pressure altitude is this elevation plus this height difference between these two pressure levels. Now what is that height difference? We know that pressure difference of 1 millibar will produce a height difference of 30 feet, approximately 30 feet, accurately 27 feet. So now, what is the pressure difference between these two data? 1013 minus 999. So that is 14. So a pressure difference of 14 millibar will produce how much height difference? It will produce a height difference of 30 into 14, that is 30 into 14, that is 420 feet. So this is 420. So now we are going to substitute the values. 25,000 plus 420 is 25,420 feet. So correct answer here is 25,000. The closest option is 25,400. Now here they have got 25,400 because maybe they have used a value of 27 feet instead of 30 feet. Okay, that 1 millibar is equal to 27 feet, but most of the times, even if you take 30 feet, that makes your calculations simpler. So with that value, you get 420. With 27 feet, you will get a value of 14 into 27, 378. So 25,378 feet. So the closest option approximate is 25,400. Next, if pressure altitude is 6,500, elevation is 560 feet, 5,660. What is QNH? So again, let's draw your airport surface. So here we have to find pressure value. In the previous question, we were given the pressure value. We had to find the pressure altitude. So mean sea level, there are two pressure data correction. Mean sea level, which is QNH. Now the elevation of airport is measured from QNH, mean sea level, which is elevation is 5,660. Okay. Pressure altitude is more than the elevation. As you can see, pressure altitude of 6,500 is more than elevation of 5,660 feet. Correct. So pressure altitude is more. That means the pressure altitude is measured from a datum which is below the QNH data. So that means standard pressure setting 1013 is below the QNH datum. So pressure altitude is total 6,500. Now the height difference between them. 6,500 minus 5,660 is 840 feet. So the height difference between these two pressure lines, QNH and standard pressure setting, is equal to 840 feet. We can convert this height difference into corresponding pressure difference. How? We know that a pressure difference of 1 millibar equals to 27 feet. So how many millibar pressure difference will be equal to 840? So that will be equal to 840 divided by 27, which is 31 millibar. So height difference of 840 equals to a pressure difference of 31 millibar. Therefore, your QNH will be standard pressure setting minus 31. So 1013 minus 31 is 982 millibar. Okay, the correct answer will be, the closest is 985. So option A. Why have we subtracted this 31 millibar? Because QNH datum is above the standard pressure setting datum. And when you go to higher and higher levels, atmospheric pressure decreases. Therefore, we have subtracted the value. If pressure remains constant, okay, so pressure is constant. The other factor, temperature, is increasing. What will happen to density? So remember, whenever temperature increases, that means the air becomes warmer and warmer. Density of air, density of air decreases. That means air becomes thin. Density of air decreases. Density altitude increases. So the correct answer here will be either option Bravo or Charlie. Let's eliminate alpha. So now look at the second part of the options. Calibrated airspeed task ratio decreases. Calibrated airspeed task ratio increases. Now calibrated airspeed is nothing but a function of dynamic pressure. Okay, is a function of dynamic pressure. So now here it's given in the question that pressure remains constant. Pressure remains constant. That means let's say there is a aircraft passing through this different parcels of air. In this parcel, temperature equals to 20 degrees Celsius. In this parcel of air, temperature is more than that, 30 degrees Celsius. Temperature has increased as given in the question. But the atmospheric pressure in both parcels of air is constant. Pressure is constant. So that means aircraft traveling from parcel number 1 and entering parcel number 2, parcel air number 2, will have same calibrated airspeed. Same calibrated airspeed. Because pressure is constant. And calibrated airspeed is a function of pressure, atmospheric pressure. So atmospheric pressure is constant, so calibrated airspeed will also not get affected. What will happen to true airspeed? Now true airspeed is a function of temperature. When temperature of air increases, the true airspeed also increases with that. Okay, when temperature increases, true airspeed also increases. For example, let's say calibrated airspeed in this example 1 is 100 knots and temperature is 20 degrees Celsius. So temperature is 20 degree Celsius. Let's use the CX3. Outside air temperature is 20 and calibrated airspeed is 100. Pressure altitude is, let's say, 5,000 feet. So what is TAS? TAS is 110 knots. TAS is 110 knots. Now in the second example, in the second parcel of air, again same CAS 100 knots temperature 30 degrees Celsius, altitude is the same 5000 feet. So, but I'm changing the outside air temperature to 30. Now, what is the true airspeed? True airspeed is 112 knots. True airspeed is 112 knots. Like I said, whenever temperature increases, true airspeed will also increase with it. Now, the ratio, gas to TAS ratio in this parcel of air is 100 divided by 100 divided by 110. 100 divided by 110 is how much? 0.9. In this second parcel of air, gas to TAS ratio is same 100 divided by 112. So 100 divided by 112 is 0.89. So what has happened to the ratio? Here in this first parcel of air it was 0.9. Second parcel of air it is 0.89. So what has happened to the ratio? It has decreased from 0.9 to a new value 0.89. So the correct answer here will be option Bravo. The ratio should decrease. The ratio will decrease. Next. Question 24. If aircraft flies with a constant Mach meter indication in ISA temperature, in ISA air mass, that means aircraft is climbing with a constant Mach number. What should happen to the ASI indicator? Now Mach meter will indicate Mach number, so that means aircraft is climbing at constant Mach number. Airspeed indicator will indicate calibrated airspeed. So indirectly this question is asking you to find out the condition of calibrated airspeed. So when you climb at constant Mach number, what happens to calibrated airspeed? Whether it decreases, increases, remains constant. So, like I said previously, calibrated airspeed is a function of atmospheric pressure, namely dynamic pressure. Now, whether you are climbing in ISA level air mass, ISA conditions, warmer than ISA conditions, colder than ISA conditions, calibrated airspeed won't be affected by temperature. It is only concerned about atmospheric pressure around it, in which it is flying. Now, as you climb to higher and higher altitudes, what will happen? Atmospheric pressure will decrease in value. So when atmospheric pressure will decrease in value, it will affect calibrated airspeed. Calibrated airspeed is directly proportional to atmospheric pressure. So if pressure decreases, it will also bring down the value of calibrated airspeed with it. Okay. So what will be the side effect? If you are climbing at constant Mach number, how should ASI indicator respond? ASI indicator should register a decrease in its value because when you climb, pressure decreases. Now, constant Mach number climb also means a constant, constant correction. Constant Mach number climb therefore also means a decrease in ISA, decrease in calibrated airspeed. Okay, so remember this. How will Mach meter indication respond if aircraft passes through a cold front when flying at constant calibrated airspeed and constant altitude? So let's say we are flying at a calibrated airspeed of 100 knots and you're flying at a fixed altitude of 5000 feet. So as given in the question, you're flying from a warm air mass. Let's say you're flying from a warm air mass into a cold air mass, from warm to cold air mass. Now let's say in the warm air mass the temperature is 40 degrees Celsius. When you enter the cold air mass the temperature there is 20 degrees Celsius. Right? Now Mach number. Your Mach number equals to true airspeed divided by local speed of sound. Okay, so if calibrated airspeed is 100 knots, altitude is 5000 feet, temperature is 40 degrees Celsius, so true airspeed of aircraft in this particular warm air mass will be how much? It will be how much? So use CX3, so TAS is equal to outside air temperature is 40, gas is 100, altitude is 5000. So true airspeed in these conditions is 114 knots. 114 114 knots. TAS in cold air mass will be 110 knots. The TAS will decrease. In warm conditions, it is more than the airspeed in cold conditions. Now, Mach number. What is the formula for Mach number? It is Mach number equals to TAS upon local speed of sound. Next thing, what will be the local speed of sound in warm air mass? It will be equal to 39.17 square root of temperature in Kelvin. So 39.17 square root. What is for temperature is 40 Celsius. In Kelvin, it will be equal to 313. So square root of 313 is 17.69 multiplied by 39.17. It is 692.9 or 693 knots. In cold air mass, the local speed of sound will be 39.17 square root of 20 plus 273, 293 Kelvin. Square root of 293 Kelvin is 17 multiplied by 39.17 is 670 knots. Now we will apply this value. So put this values in the Mach number formula. So here Mach is TAS divided by local speed of sound. 114 divided by 693, 0.16. Here Mach number in the cold air mass TAS divided by local speed of sound. So 110 divided by 670 is again 0.16. Same value 0.16. So what has happened to the Mach number? 0.16, 0.16. It is the same in both kinds of air mass. That means the answer to this question is option Charlie. Mach meter indication or the Mach number will remain the same, will remain constant if aircraft passes through a cold front at constant calibrated airspeed and constant altitude. Now here I have found the Mach number using this formula manually. You can also use the calculator and directly find the Mach number. That will save your time. But I have explained each and everything here so that your concept gets perfect. Next. Aircraft was over A, Alpha at so and so time, flying to B, Bravo. Distance between them, TAS, wind components are given outbound, homebound. What is the estimated time of arrival for reaching point of equal time between these two positions? Right. So first we will find distance to point of equal time, which is the total distance divided by O plus H. So let's find out ground speeds. Now we have point A, we have point B. The distance between them is 2900 nautical miles. Point of equal time, let's say it's here, critical point. Now aircraft going outbound from point A to point of equal time is getting a tailwind. Outbound, it is getting a tailwind of plus 55 knots. A tailwind of plus 55. So ground speed will be true airspeed plus tailwind. What is true airspeed? True airspeed is 470 plus tailwind of 55. 70 plus 55, 525. And coming homebound, that is from point of equal time back to your position A, ground speed will be how much. Now coming back, you're getting a headwind. So mean wind component back is minus 75 knots. You're getting a headwind minus 75 knots. So ground speed will be true airspeed minus headwind. So true airspeed of 470 minus headwind 75, which is 395 knots. 395 knots. Now let's employ the ground formula. Distance to critical point is equal to total distance multiplied by homebound speed divided by outbound plus homebound. So 2900 multiplied by 395 divided by 395 plus 525. So final answer is 1145,500 divided by 9. 1245 nautical miles. Time to critical point is distance to critical point divided by outbound speed. So 1245 divided by outbound speed 525. That is 2 hours 22 minutes. So you will take 2 hours 22 minutes to go from point A to point of equal time. Now your departure time is 1435. Journey time is your flight time is 0222. So your arrival time will be 1435 plus 2 hours 22 minutes, 16 hours 57 minutes. 16 hours 57 minutes. Option Bravo. Question 27. Distance A to B, ground speed outbound, ground speed homebound is given to you. What is time from point A to the point of equal time? So direct use the formula directly because we have been given all the values ready-made. So distance to critical point is dh upon O plus h. So distance 2700, homebound speed 515 divided by 515 plus 465. 980. Numerator you will have 2700 multiplied by 515, 1390500. So that is equal to 1419 nautical miles. Time to CP will be distance to CP divided by outbound speed. 1419 divided by outbound speed is 465. So 465, which is 3 hours 3 minutes. 3 hours 3 minutes. 3 hours 3 minutes is nothing but 183 minutes. So option A. Question 28. If there is a 12 knot increase in headwind, by what amount must the rate of descent be changed in order to maintain a 3-degree glide slope? So the formula is change in rate of descent equals to 5 multiplied by change in ground speed. Change in ground speed. So 5 multiplied by change in ground speed is 12 knots. A change of 12 knots. So 5 into 12, 60. So rate of descent change will be equal to 60 feet per minute. It will be 60 feet per minute. Now, whether you will increase your rate of descent or decrease it in headwinds, in headwinds, your aircraft tends to come down, that is to sink, tends to descend faster. So the solution to this thing is you will have to decrease this trend, you will have to decrease your rate of descent. So correct answer is it must be decreased by 60 feet per minute. Option Charlie. Next. In tailwinds, your aircraft tends to remain suspended in the air. It refuses to come down. So in that case, in tailwinds, you will deliberately increase your rate of descent. But in headwinds, you will decrease it. 850 per minute equals to how many meter per second? Now, so this is a two-step process. 1 knot equals to 101.3 feet per minute. So 850 feet per minute will be how many knots? It will be equal to 850 divided by 101.3, 8.39 knots, approximately 8.4 knots. Now step number 2, 1 knot equals to 0.515 meter per second. So 8.4 knots will be how many meter per second? It will be 8.4 into 0.515, which is 4.3 meter per second. So option Charlie, 4.3. Question 30. A revenue flight is to be made. Revenue flight is a commercial flight. The following are the airplane's structural limits: ramp mass, takeoff mass, landing, zero fuel. Takeoff and landing mass are not performance limited. Dry operating mass, trip fuel, taxi fuel, reserve fuel, alternate fuel are given. What is the traffic load that can be carried? Step 1. Make 3 columns. One for takeoff mass, the second for zero fuel, the third for landing mass. In the takeoff mass column, you are going to write the maximum takeoff mass limit given to you, 69,300. So 69.3, write 69.3. Zero fuel mass formula is zero fuel mass, maximum zero fuel mass plus fuel on board. So zero fuel mass is 52,052.74. Fuel on board. What is fuel on board? Now here the fuel on board is takeoff fuel. That means the fuel in the fuel tanks when your aircraft is ready for takeoff. It is aligned or lined up with the runway. So in at that point of time, the fuel remaining in the fuel tanks will be all the fuel minus taxi fuel. So taxi fuel is subtracted from that total because you are going to use or spend all the taxi fuel in taxiing your aircraft from parking area to the runway. Okay, so you don't consider that. Apart from taxi fuel, you are going to include all other fuel parts, fuel components like trip fuel. Okay, then contingency final reserve fuel, and then you're also going to include alternate fuel. So now add them. Trip fuel is 11,500, reserve is 1,450, alternate is 1,350. So 11,500 plus 1,450 plus 1,350, 14,300. So 14,000, 14.3. So 14.3 plus 52.74 is 67.04. Landing mass is maximum landing mass plus flight fuel or trip fuel. So what is the maximum landing mass here? 58,900. 58.9. Flight fuel or trip fuel given is 11,500. So 11.5. 58.9 plus 11.5. 70.4. Now your regulated takeoff mass will be that value which is the lowest of them all. So the lowest value is 67.4. Step 2. Payload will be equal to regulated takeoff mass minus DOM plus fuel on board. Now what is regulated takeoff mass? 67.04. Dry operating mass is 34,930. So 34.93. Fuel on board is 14.3. So 67.04 minus 34.93 plus 14.3, that is 49.23. 17.81 या फिर 17,810 kg. Option Bravo. So this is how you do it. Simple. So this ends a lecture. I hope you have understood all the 10 questions that I have solved, explained. If you have any doubts, any comments, feedback, suggestions, let me know in the comment box of this video lecture. I wish you all the best. Share this video with your friends. Subscribe if you haven't yet, and hit the like button if you have liked this video lecture. In my next video, I will do the next 10 questions. So don't miss that.